We'll revise a little bit on the SN graph. This one is crack length y-axis versus number of stress. So if you have this kind of sample, and you're pulling with the tensile loading and compressive loading, so the arrow will be up and down. So assuming stress number 2 is larger than number 1, okay, the stress number 2 larger than number 1. So as you can see here, this two blue line, when you pull with the higher stress, the object will fail earlier compared to the second one. Okay, so if you pull stronger, this one will fail. And number 1 here, stress number 1 is smaller, so you pull at a smaller force, the curve will take longer time to fail. Okay, yeah. So as you can see, this we can observe these three things on the graph. So when the crack length over here, crack length is small, the fatigue crack growth rate, the A, the N, or the we call it the A is a gradient of the curve. So the gradient of curve will be small compared to this one, right? And the crack growth rate, the A, the N, increase with increasing crack length, right? This is number 2. Number 3 is if you increase the N cycle, increase the crack growth rate. So if you increase further, you see the curve of the line here also changing. Okay, so means the number of N here, if you increase, the slope will become steeper. Okay, the slope becomes steeper. So the A over the N is the slope of this graph, A versus N. Okay. So from this curve, we can plot, when we plot Y versus X, normal graph. When we have normal graph, if you write y, x, and let's say we have the same curve like what you see on the screen. So here we can write y, y inverted with a function of, let's say this is a stress, function of stress and A. Okay. So this is function of stress and y. Let's say this is A, then this one is A. So we can relate the slope with the function of stress and A. Then you know that in your mathematics, if you can link the A with linearly with the function, we can convert this one into constant A. So the N, you copy, you change this symbol into A, and the change of Km, A is your slope, your constant, M also your constant. In this curve, you know that this is a quadratic curve or can be a polynomial curve, but the lowest exponential we can get is quadratic curve, right? So in the form of polynomial, so A, delta Km. Again, what is delta K? Delta K is differences of your stress intensity. You take maximum minus minimum. Okay, so this is what we learned this morning. Kmax equal to stress max square root of pi A. Same with minimum. We only change the stress into minimum. So when we have range of K, we take this one minus this one. Okay. Then we apply for log because we have an exponential here. We want to move the exponential to the front. So we log both sides in mathematics form. So log something and log something, we can move the m to the front and chain it to the y equal to mx plus c. So your y, you plot log something equal to m, log your x, and the intersection of y. So you will see this kind of graph, like this morning, we introduce you this graph. So you have three regions, region 1, region 2, region 3. Okay. So since K delta K equal to Y stress square root of pi A, so when you multiply this K with the M, so each one of it will have, you have a bracket of M, so your Ym stress M, pi become M divided by 2, A divided also power M divided by 2. Okay, so when you take this one, substitute back here, you arrive at a new equation, and you pull your dn to the right hand side. You have d something equal to something dn. So dA, we know that when we see dA, dn, we will add the integration sign both sides. So it becomes an integration procedure. Okay, and so on. The derivation continue. So this one I will just show you on the slides. Okay. So you just continue doing the integrations things. And in the end, you arrive at this equation, right? This equation. So example 3, you go home and see this one, right? Because it's just an application of the equation, right? So dn the cycle is given, and you're applying the A over the n equal to K delta Km. So this is your homework lah. So it's just application of the equation. Okay. So this is your homework lah. Go home and have a look into this one. Okay. And application of this one. Okay. So if this one come out, sure, I will give you in the appendix or I'll give you in the question. Okay. But you have to understand what is AF, A0, and so on. Okay. All right. Then another one is the plastic deformation. When plastic deformation, we call it creep. Creep. For example, the turbofan behavior. Right. So what is creep? Metals under a constant load stress may undergo progressive plastic deformation over time. It's time dependent. This time dependent strain is called creep. Means deformation happen over the time. Maybe at a certain time, you by physically you are unable to detect. But maybe when you use this blade for 1,000 hours, so after 1,000 hours, you might see that the fan shape actually changing. Right? So you'll see this creep curve. By y-axis is your strain. Strain is a deformation ratio versus time. You get a curve like that. So you have primary creep, secondary creep, and tertiary creep. You have 3 regions for the creep: primary, secondary, and tertiary. When it becomes the end of tertiary, the things will break. Okay. Okay. So if you understand the curve shape, y equal to ax squared plus bx plus c. If your a is positive, you are seeing a smiling face. If your a is less than 0, you'll be seeing a sad face. So by using very simplified method, you know that if you look at this primary creep will be give you a smiling face, where your a, y equal to ax squared, your a will be positive plus something, right? But it's a quadratic positive a. When it comes to here, secondary, you can assume that it's almost a straight line. Almost a straight line. Then after the end of the second creep, it become a sad face. Not sad face, smiling. The first one is sad face. Second one is a smiling face, where it take this form. Okay, so the first one, a correction. For the primary creep, is a set phase, so it's your A will be negative. Y equal to ax squared, your A will be negative. But when it comes to secondary, it become linear. So when you're linear, you can do the slope y equal to mx plus c. Then here is a smiling phase. Smiling phase is your A more than positive, positive. Right. Okay. Okay. So here you have a linear form here, right? So secondary creep, the creep resistance will be the highest. Means in here, the material was try to stop the deformation here. Okay. Then at the end of this one, the material lose power already. It kind of let go. I cannot control you already. So it try to let go. So it will fail very fast. Okay. Tertiary creep. So the rest you read from the slides. Okay. So tertiary creep here is the necking phenomena that you see in your experiment, especially for aluminium. But for the very strong material like the fan blade, this is a fan blade, it will fail at this here, and it will twist it and it will elongate it like this one. The necking will be happen. Okay? So you spin at one. So like every time when I sit by the jet, because I know all these things, I have a concern, but I think I still believe the engineering in the industry. So this kind of accident won't happen nowadays, because there is almost like every flight, the aircraft landed, the pilot will check one go, the engineer also will check one time. So unless both of them do not do their job, then this kind of thing will happen, right? Okay, okay, the rest you read. Okay. So creep test. Okay, at least you know how to do a creep test, even though we don't have the equipment at the moment. But since you're taking engineering dynamics, engineering material, you should know how to do creep test.
In this video, we will be demonstrating the creep testing machine, the SM1006, allowing engineering students to practically study the phenomenon of creep under different conditions and in various materials.
It's a scale down equipment, but in the industry,
the creep testing machine is about simplicity. It uses a simple lever and weights to apply load to lead and plastic specimens, and an ice pack that can be added to a chamber to change the temperature. Readings can be gathered manually using a digital displacement indicator, or digitally using TechQuipment's versatile data acquisition system. This is one of the many experiments within the materials testing and properties range from TechQuipment that allows you to witness the normal breaking load of lead and different plastic specimens over a fixed time. Look at the relationship between breaking load and time for lead specimens. Create time extension curves to show the three phases of creep, that is primary, secondary and tertiary. You can also look at the effect of temperature on the creep rate and establish the creep rate for different specimens. Let's take a closer look at the creep testing machine. Here is a long lever, which is also referred to as the load beam. This has a mechanical advantage of 8:1 with a pivot point at this end. This pivot is a bearing for very low friction. At the short end here, students fit specimens, and at the other end of the load beam, loads are applied on top of the weight hanger using the set of weights supplied. I'll show you how all this is done shortly when we look at one of the experiments. All of this is mounted on a base plate that is labelled with the effective mass of the arm. Just below the weight hanger on the base plate, there is a rubber mat to reduce the impact energy of the falling weight hanger when a specimen fractures. Moving on to the forms of measurement. Over here there is a digital displacement indicator that measures the extension of the specimens. If you're using VDAS for data capture and analysis, you plug the lead into this and connect to a VDAS hardware unit, which is then connected to a computer with the free to download software running. Temperature affects creep. This is why the creep testing machine has a clear enclosure over the area where the specimen is mounted to create an isolated zone to help keep the temperature constant while adding the included ice pack to lower or raise the ambient temperature. A thermometer inserted through the top of the cover measures that ambient temperature. There are additional components included to allow you to measure the temperature using VDAS, including a thermocouple and a thermocouple transmitter. Now we're going to look at the first experiment that look at creep in different material stresses and temperatures. Set up like this, we put one specimen in. Let's start with polypropylene, fixing it in place, and then you put the clear enclosure on over the top. Wait 5 minutes for the temperatures to stabilise and then record the temperature. Now it's time to start applying the load with the weights and recording the weights, giving the time between applying loads before recording the results, as shown in the user guide, to allow creep to occur. It's then a matter of taking recordings every 30 seconds. For some materials, this is going to take hours, which is where VDAS really becomes very useful. Go through all of these specimens with different weights and then repeat using the cool pack, both cooled and heated, to examine the impacts of heat on the specimens. When done, you can create a chart of specimen extension against time and calculate the curve gradient to establish the creep rate. Another experiment in the user guide takes you through elastic extension and creep recovery in plastics, testing the polypropylene specimen at room temperature. By going through the steps in the user guide and charting the results like this, you can use Young's modulus to predict the elastic extension and recovery. For more information on the creep testing machine and other experiments in the materials testing and properties range from Tech Equipment, click on the links below. Thank you for watching.
Find the stress concentrator. So the creep test, you'll find elongation or strain with time. So you'll see that the sample will give you this behavior. So here you know that you have primary, secondary, and tertiary. So you have 3 stages there. This one. This one. Yes. No, that one is the blade, how the blade behave. So let's say this is the blade. So this one rotate, right? So you know that when you swing a ball, you'll feel that the ball is actually go outside. So there's a force pushing this blade out. So when you have this pushing out, actually is the same as your sample. You're pulling both ends. Yeah, can you imagine? No, there is a load, there's a moment pulling that one out. You don't confuse with the centrifugal force that the race car and spin, there is a centrifugal force AN here. This is acceleration, not force. Okay, this is in your engineering dynamics. Right. So don't with the force that pulling the blade. So but the blade will act as what you learn in your mechanical properties, tension, pulling at both ends. Be the same. So that's why you see the experiment just now in the video, it was pulling tensile loading. So you watch lah. Then okay. So how to find the minimum creep rate for this sample? You take the gradient of this one, the gradient of this straight line, dy dx. So dy is your strain versus time. This is a creep rate. So here you take 0.003 minus 0.002, take this one 200 hour, and this one is 1000. The time is 800 hours. Change the hours maybe to time, to second if you need it, right? If not, then put remain as hour. So in this case, if we put everything in, our creep rate for this sample on this graph is very simple. Just find the gradient of the graph on the middle section, secondary creep. So you will get 1.25 10 power 6. In this case, inch per inch, because here the unit is inch to inch, right? But nowadays, our experiment all in unit SI. So you'll see mm over mm over hour. Okay. So this is another example, but still you see straight, and because it take a very long time, so usually we'll use a log graph. You see a log graph with a scale to see the straight line. Okay, so this is another one, also same. Okay, so another or the last important formula for this chapter 8 is graph presentation for the creep and crash stress rupture using LM parameter, Larsen-Miller or LM parameter, give you by this formula, right? So P LM equal to T log TR plus C. TR is stress rupture time, constant. C is a constant. T is in Kelvin. Right. So there are two types of equation, the one on the middle here and the one at here. If in terms of Kelvin hours, and there are two equation. The one that below here, if the question give you Rankine, you use this one. You use the constant value 460. If you are using Kelvin hour, then you use this one. Normally we'll use the middle one, this one. Okay. So these are the graph that we use to do LM parameter. In fact, when you see this graph, you should be happy. Why? Because all the formula is given on the graph. For example, on this graph, you see Miller parameter P equal to T something. There's a formula here. You just straight away pull this formula and use it. Same is here, but don't use the wrong one. The top one is in Celsius, below one is in Fahrenheit. So don't use the wrong one. Usually you just need to go and find Celsius one. Okay. Okay. So there are two formula here. Choose the one in give you Celsius. Then the one the y-axis is stress. Right. Okay. So let's say we ask you this one in your test 2. So use the LM parameter plot as stress 207 megapascal. Determine the time to stress rupture at 982 Celsius for directional solidified alloy CM247. CM247 is here. 247. Alloy 247 here. CM247. The point arrow is this one, this line. Okay, so it depends on what question asks you. So you just need to follow the arrow. In this case, the question asks you alloy CM247, which is the center line. Okay. So in this case, you use Celsius. So again, copy the equation from the graph. You don't need to memorize one. You see this one, normally you see the equation. So here, you only need to put in all the value. So at stress 207, you extend the line to the line here, and then either go up or go down. In this case, we are using Celsius. So you go up, pull your graph up there. So when you pull your graph up there, you're seeing your LM parameter is somewhere 27 something. Okay, so it's 27.6 something, 10 power 3, 10 power 3. See here. Okay, the unit is on the graph is 10 power 3 Kelvin hour. 10 power 3 Kelvin hour. Okay, how you know the unit? If you look at this formula, you're dealing with temperature, and you already convert temperature into Kelvin. So the unit will be Kelvin multiplied by log time plus 20. This is time in the unit of hour. So unit is Kelvin hour. Huh? You rearrange the equation, you'll get your TR equal to something. Difficult part is you might already forget how to reverse the log into this one. Okay, so normally in the log 10. Okay, so these are the other example lah for LM parameter. So this one also same. So calculate the time caused by 0.2% creep strain. This actually is a bonus question because everything is on the graph that have equation. So this question asks you to find creep strain, 0.2% creep strain in gamma, titanium, aluminium, TiLi at a stress of 40 kilo square feet at 1,200 Fahrenheit by using diagram. Comparing ROC and so and so. So this one basically you are using this graph, and because you're using Fahrenheit, so just follow the Fahrenheit value and go to find the TiLa, which is this blue line. So you go here at the stress of 40 kilo KSI. So this one is in a log scale. So this one is 1, this one is 10, and this one 1, 2, 3, 4, 5, 6, 7, 8. So you need to convert all this line accordingly lah. Okay, so you follow the working, you will get the time. Okay, with this we conclude chapter 8. Okay. This is actually the okay. Yeah, I will upload. Yes.